Okay, good afternoon. Can you hear me?
Yes, Prof. Good afternoon, Prof.
Okay. Last 2 weeks, I already discussed with you the pseudo random binary sequence. Okay. Several maximum length sequence. Okay, we can generate from the feedback configurations given, which is shown here. Okay, so we have a lot of maximum length sequence, which is given by capital N equal to 2 power of small n minus 1. So we can generate these PRBS test signals by using hardware and by using software. Okay, so this is the hardware designs. Okay, and the software designs by computer algorithms. Okay, to generate the signals from the computer or Arduino. So this PRBS have the autocorrelation functions and power spectral density, which is a very important analysis of the input signals. Okay, so let us consider the first values of tau equal to k delta t, where delta t is the sampling time or sampling interval. Okay, k is an integer. So let values of the sequence for the successive intervals delta t to be x1, x2, x3, and so on. So the autocorrelation function of the PRBS is by taking the sample of xj and xj plus k, which is the same version signal itself, but shifted by k. Okay, so this is the original signal. This is the same signals, but shifted by k. Then the autocorrelations will equal to a square divided by n, which is multiply the number of matching digits, number of differing digits. So we can define it as minus a square over n if k not equal to 0 and is equal to plus a square if k equal to 0. Okay, so this one can be shown, okay, by considering the area of changes of the autocorrelation function, okay, at this point, okay, and it's shown in the figure 7.15, which is here. Okay, so you can see that this is the autocorrelations of the PRBS signals. So it will repeat after n delta t. So what is n? N is 2 power of n minus 1, which is the maximum length sequence. Okay, so this is the a square, which is at 0. Okay, and delta t on the left and on the right, and between the datum line and the autocorrelation function is a square divided by n. And as t delta t towards 0, n becomes the large or the maximum value of the ACF, which is closer to the true periodic white noise, as shown in the previous figure. And this is the power spectral density, PSD, of the autocorrelation functions. Okay, where you can see that maximums is at frequency equal to 0. And then the first cutoff, okay, of the PRBS signal is at 2 pi divided by delta t. This one is the second cutoff. And 3 dB, okay, 3 dB is the bandwidth of the PRBS, so which is equal to 2 pi divided by 3 delta t. Okay, so usually 3 dB is referred to the bandwidth frequency. And autocorrelation function and power spectral density of PRBS, yeah, usually this one is for periodic white noise. but this one is for the of the PRBS signals itself. So it tallies a little bit, okay? Maximum and here, can then repeat again according to the ACF. Okay, so you can compare the ACF and the PSD. Okay, for the binary functions, okay, which is more or less same as this one, okay, figure 7.15. So you can see that the power spectral density of the PRBS, as shown in the figure 7.15, differs from figure 7.8, okay, in one respect, where it is a line spectrum and not a continuous spectrum, okay, between 7.8 and 7.15, okay. This occurs because the lowest frequency component in the PRBS signal is that corresponding to the period 2 pi divided by n delta t radian per second, and all other frequency present are integer multiples of this value. So that is the only difference between the 7.15 and 7.8. So further details you can read from the book chapter that I attached via WhatsApp. So what is the advantages of PRBS compared to other test signal, step signal, sine wave, and so on? So the advantage is that the binary nature of the signal simplify the cross correlation calculations, which is either 1 or 0, since the multiplication can be replaced by simple gating, okay, of the output time function and its inverse. And the binary signals is easy to generate using hardware or using a computer programming and introduced into the system by injections. And the constant delta t, the intervals, will avoid the distortions. So usually delta t is 1 millisecond, okay, in practice for system ID. So which can occur with attempting to rapid switching, which can be required with a completely random binary signals. And the PRBS signal intensity is low, with energy spread over a wide frequency of range. Hence, it is suitable for forcing functions. Okay, so the energy is separate in a very big range of frequency. So easy for you to capture more frequency in the region of interest. Okay. And this will make the plant operating normally, okay, even though we have a little disturbance from the operating conditions. Then the power of the noise can be arranged to be in the band of frequencies of interest, that I say so, okay, because by choosing the appropriate delta t and n. Delta t is just the sampling time or sampling interval, and n is the maximum length sequence, or 2n minus 1. Somehow, the input autocorrelation function is calculated to its full accuracy by correlation over one period. Hence, the average out effects of system noise, so we can avoid noise when we apply cross correlations. Okay, and then the smaller of the PRBS amplitude relative to the system noise, the longer the averaging time required. That's why we have, if we have the PRBS signal like this, so it's very small, so we increase the amplitude so that we can differentiate between the noise, okay? The amplitude of the signals is more significant compared to the noise disturbance as in blue. If we don't increase the amplitude, so you can see that in this case, the noise and the real PRBS signals cannot be differentiated. So we have to remove the noise in order to get the autocorrelations of the PRBS signals. So what choice do you have in order to design the PRBS parameter? So to ensure the PRBS input has a flat power spectrum over the system frequency range, so we choose the amplitude of PRBS signal should be as large as possible. Okay, let's say 5 volt for logic 1 and negative 5 volt for logic 0. Okay, so it is 10 volt peak to peak, okay, for the input signals. Okay, this is vital, this is important, okay, without driving the process to be a nonlinear. So we try to increase the amplitude, okay, from small amplitude to big amplitude. And delta T should be approximates 1/5 to 1/10. So 0.2 and 0.1, okay, of the fastest process time constant. Okay, so what is time constant? Time constant is when the response is 63% of the final value. Okay, so if the final value is 1 volt, so the 63% is 0.63 volt. Okay, and the period of the PRBS T, which is equal to n delta T, should be just greater than the system settling time. So what is settling time? Settling time is the time where the response will reach plus minus 2% of the final value. Okay, so if the final value is 1 volt, so plus 1% is 1.02, minus 2% is minus 0.98. Okay, so in between that. So we look at examples here. Okay, so system under test is a second order system in the presence of noise. So what is second order system? Definition is system that have two poles. So that is definitions of second order system. The input function or forcing function is PRBS signals. The undamped natural frequency omega n is equal to 6 radian per second. So damping ratio is zeta equal to 0.3. So what is the damped natural frequency? Omega d. Omega d is omega n 1 minus zeta square. So somebody help me. What is the value? 1 minus 0.3 square. The value of omega d. Omega d is damped natural frequency. How much? 6 multiplied by square root 1 minus 0.3 square.
5.724.
5.724 radian per second. Right, and then the block diagram of the system being identified is shown in figure 7.16. So this is the way we conduct the experiment. So this is the unknown system. Okay, I can consider it's not a black box, but it's a gray box. Okay, because we know already the criteria, which is the second order. Okay, second order system, and then the omega n is equal to n. Zeta is equal to 0.3. Okay, so most of the important parameter is known. Okay, then you put the normal input here. Let's say 1 volt, and then this is the PRBS test signals, and the dotted line is the boundary of the system being tested. Okay, and then this is the disturbance signals that enter to the process. Okay, so disturbance is somehow is out there. Okay, so disturbance will enter here. And of course, the Y is the output, U is the input. Okay. So in the absence of noise, when we assume there is no noise, the system can be subjected to an input change in the form of step or impulse functions. So we can do pre-test. Okay, we call it as a pre-test. Just take the signal generator, then open on the square wave. So then inject the step inside or impulse functions and see the response. So when we do this pre-test, okay, so the response curve for the step magnitude unity and the impulse is the magnitude of 0.25, okay, which is here. Okay, so this is the unit step response, the dotted line, and this is the impulse response, which is delta equal to 0.25. Okay. So comparison of this curve with the standard response in figure 4.7 will estimate the value of omega n and zeta. That's why when we do this pre-test and we obtain this response of the step and the impulse, then we compare these two response, transient, unit step and impulse, compare with the standard curve. Okay, this is a standard curve for second order system to a unit step and unit step and the unit impulse forcing function. So you can see that the zeta is that we choose just now is 0.3. Okay, so it is equal to with the 0.3. So if you see the curve there, it goes up from 0, then up to 0.3, and then oscillate, and then get the final value. Okay, so that is pre-test. So from pre-test, we obtain the zeta, which is 0.3. Okay. Then we achieve omega n, then we achieve omega d. So now we are getting into business by injecting 63-bit PRBS signals. Okay, so 63-bit PRBS signals is where n is equal to 2n minus 1, 63. Okay, so 2n equal to 64. So what is the value of n? What is the value of n? Somebody?
8.
8.
8. 6.
Okay. Oh, 6. 6 or 8?
6. Oh, sorry.
6, eh? So meaning that we need how many shift register in this case? We need 1, 2, 3, 4, 5, 6 shift register. Okay, until SR6. Then you can compare with the see this one, okay, 63-bit design, okay, 1 XOR 6, 5 XOR 6, okay. One XOR 6 or 5 XOR 6. Then you can generate the signals. So interval is delta t 0.1 second. Okay, it's about 10 millisecond. Okay, 1, 2. It's used as the input excitations for system ID. Then figure 718 shows the form of PRBS input and the resulting system output in the presence of noise. So you can see that this one looks very beautiful, clearly, okay, PRBS, and output, okay. So this is input, okay, no noise, excellent, okay. the bit interval and the maximum length sequence can be chosen on the basis of preliminary estimate of the order of the magnitude of the dominant roots of the system. Confirmation through inspection by the correlation function. So in this case, 5 and 6 can be as a feedback, goes to the input, and SR6 is the output. Okay, and of course, each shift register must be powered by clock pulse. So we have remaining B and C. So in the presence of noise, okay, on the system output, comparison method with the standard curve is not suitable anymore. So we cannot rely anymore if the noise is there, because we are related to the signal to noise ratio. Okay, if the noise is very small, so we still can apply standard curve. Okay, but if a noise is very big, okay, and the SNR is very small, so we have to think twice, okay, because the system have a full noise inside, so we have to be very careful about that. Therefore, statistical testing can yield an impulse response curve with the minimum disturbance to the system. That's why we apply statistical testing, okay, correlation testing. So 718 shows a typical sample trace of the output response of the system in the presence of noise and nominally constant input. Okay, so you look here. So B is the without PRBS. So this is the noise. Okay, no PRBS. This is the noise. And this one is the noise plus the PRBS signals together. Okay, so together. So this is data taken about 12 seconds. Okay, for the system, the gray box system with the input excitation PRBS 63 bit. So figure C just now, this one, okay, shows the response of the system to the PRBS signal in the presence of noise. And figure 718B is the normal noise output without PRBS. And 719 shows the autocorrelation functions of the input and output signals based on the block diagram of a system being identified. So we applied the computer program for autocorrelation, okay, and then we try to correlate psi xx tau and psi yy tau. Psi xx is for the input, which is the PRBS, okay, x and y is the output. Okay, both give a different autocorrelation functions, okay, one input, one output. And then we applied autocorrelation for noisy system forced by PRBS and in the absence of PRBS input, the noise actually, okay, so it fulfill and the expected results that we want. Psi xx is the autocorrelation of PRBS signals, okay, and it fulfill the form theoretically expected. Psi yy tau is the autocorrelation for the system forced by PRBS in the absence of noise. Okay, no noise. Shows a reduction in signal power, which is less than half of the input power. Then second, psi yy tau is the autocorrelation system for noisy system forced by the PRBS input. And finally, the third one is psi yy tau is the autocorrelation for noisy system in the absence of PRBS input, which is significant component of the signal which approximately equal to white noise. Okay, slide 59. So let's go to the real examples here. Okay, so we have examples, correlation curve. For each curve shown was carried out by a time duration of 130 seconds. So this one is 1 minute, 1 minute 10 seconds. Okay, experiment period. which correspond to about 20 periods of PRBS. So you have one period of PRBS, then you repeat again about 20 period, okay, so that we can get a longer PRBS signals. A longer period of correlation would be help to smooth out the curve at the larger values of time shift tau provided by the dynamics characteristic of the system being tested remain unchanged over the longer time span involved. So the correlation of the system with the signal of PRBS input should yield a good approximation to the impulse response of the system, and it will shows you a typical trace for the CCF with and without the system noise. So first we applied auto correlation system between the noise for the noisy system after 130 seconds period correlations. So you can see that in the absence of noise, the dotted line and the straight line really fulfill, okay, the expected results from the true data, okay, which is the solid line. And this is proof that the noisy system has been removed from the calculations, okay. So just left here only. Okay, so that we can see that it is very small and accepted. So second psi xy is the CCF for the system in the absence of noise. Third one is the psi yx tau, which is the CCF for the noisy system. Okay, and figure 7.21 shows the power spectral density curve for the input and output signal plotted against a logarithmic frequency scale. So you can see here the response from the case study, right? So this is a log scale of the power spectral density, okay, of the PRBS. So you can see that phi YY, which is equal to power spectral density for the system forced by PRBS input of absent of noise, okay. Noise equal to 0 line. The psi XX omega is the power spectrum density for the PRBS input, and psi YY omega is the PSD noisy for noisy system in the absence of PRBS input. And again, we try to plot into the boat plot, which is using a gain and phase. So you can see that the system is go up and then goes down with the slope of minus 40 dB per decade. So meaning that it's confirmed it is a second order system, and it goes down here but settle at minus 180 degrees. So confirm that the data given is a second order system. Right, we go to the examples, okay, from a book in the attachment. A control system element was tested by the cross correlation method using a PRBS input of a sequence of 127 bits. Okay, so 127 bits, maximum length sequence, and 2 power of n minus 1, 1 to 7. So n is equal to
7.
7. So you need a 7 shift register in order to generate it. Bit interval 20 milliseconds. Okay. And the level is plus minus 2 volts. So plus 2 is equal to 1, minus 2 is equal to negative 1. So the resulting input-output cross-correlation is shown in figure below. So this is the results. We have 2 lines. One line is the original one. We call it as the uncorrected CCF. The second one is the corrected for 0 error, meaning that our measurement is not up to 0. So we must move it so that it starts from 0. Okay. So they're easy for us to do the calculations. So what now is the number of shift register? N is equal to 7. And what the feedback for 127, which is the S4 XOR SR7, obtain the transfer functions of the system. Right. This is the figure given. The original one is the uncorrected, but since it's not start from 0, okay, starts from negative, so we have to pull up this graph. Okay, we have to pull up so that it starts from 0. By inspection, the response appears to be a decaying sine wave. So if you look here, decaying sine wave, okay, is a decaying sine wave. The cross correlations settles at the value of minus 0.064 V square, where which is over here. Zero point 0.064. So what we do is, in order to start from 0 instead of minus 0.064, so we add all readings with 0.064. Okay, at all point. Okay, so that we can get the graph started from 0. Okay, which is resulting in the corrected graph. So the corrected graph has 0 crossing. Has 0 crossing at delay 0.77 seconds and 1.52 seconds. Giving this almost equal half cycle, will average 0.76. Okay, which is 0.77 plus 1.52 divided by 2 will produce 0.76. Solutions. So this is a result indications, is a decaying sine wave instead of cosine. And the suitable expression curve fit is using this one. Can be fitted to the curve. So the transfer function determination is, first you calculate the cycle time, which is 2 pi divided by omega. Then 2 pi over omega is 1.52 seconds. Okay, 1.52 seconds, which is the 1.52. It's about here. Okay. So an expressions of C exponent minus AT sine omega t can be fit to this curve. Okay. So it fit this curve. So we have to find the C, you have to find the A and omega. So 1.52 equal to 2 pi divided by omega. So find omega. So we get 4.13 radian per second. So the quantity A, which is at here, minus A, okay, is found from the delay between successive peak, which is 0.76. Okay, so the height of the first positive peak is 0.405, and the depth of the first negative peak is minus 0.04. So that's why you take this ratio 0.04 divided by 0.405 equal to exponent minus 0.76a. Then use natural logarithm on the left and on the right. Okay, so you can find the value of A is at 3.05 per second. And the value of C can be found from the value of the cross correlation halfway across the first half cycle, which occurred at 3 equal to 0.38 seconds, correspond to the cross correlation coefficients, which is 0.32. So we equate 0.32 with C equal to exponent minus 3.05 and 0.38 multiplications. Then we will get 1.02 V squared. Okay. So after fitted an expression to the curve, so the system impulse response to an impulse of the strength V squared times the bit interval, which evaluate 2 multiplied power of 2 multiplied by 0.02 equal to 0.08 units. And the response to unit impulse is therefore 1 divided by 0.08, which will produce 12.75 exponent minus 3.05 t sine 4.13 t. Then we apply a Laplace transform for these expressions. Okay, so we will get this equivalent to this. Okay, so therefore for these expressions, we take a Laplace transform, so you will get 57 over s squared plus 6.1s plus 26.4. So when we verified through MATLAB programming, we get the same signals, okay, as shown previously. Okay, here you can see that the difference is there. Okay. So it really complement each other, okay, which is 0.2 at the peak. Okay. And this one is 0.2 as well. Right, so we have some questions for you to question 36, okay, for you to have an exercise and try to solve it, okay. The answer is given there, question 37, okay, and the answer, okay. Time is minutes, all right. And I give you two book chapter attachment, okay. So you can read that in order to understand the slide, because the slide is very brief, okay. So you read the two book chapter that I attached, and behind it there is the tutorial, and behind the tutorial is the solutions for the tutorial given in the book chapter. Okay, guys, is there any questions? I have a meeting at 3 o'clock. Any questions?
No, boss.
Okay, if there is no question, I'll see you again on the Thursday, 11 a.m. Okay, thank you very much.
Thank you, Prof.
Thank you.